After we've looked at slipping and tipping, let's do an example next. So let's say example slipping and tipping. Slipping and tipping. Let's see what we have. Let's do another box because we like boxes so much here. Let's say this is our box. Our box is sitting on a surface. Supposed to be, well, let's make this a little more flat surface. Otherwise our problem becomes a lot more difficult to solve. There is our surface. We will say that in the contact between the surface and the box we have a friction coefficient of 0.5. We'll say the box has a mass of 200 kilograms. We will say the box has a width of 1.2 meters. 1.2 meters. And we say we have a force acting on it, a force P, and that force P acts at an unknown height h. Like that. And now we want to know what is the strongest force that we can apply here. So what's the largest P that's acting horizontally for which we get tipping, right? And then what is the height at which we have to apply it to get tipping? All right, so first we have to figure out, right, once we know what the largest force is, it's going to be easy to find h based on the moment, but we first have to think about what the largest possible force is. Well, the largest possible force to get tipping is, of course, the same force that we'd get for slipping, right? Because anything that's larger than that, if my tipping force would be higher than the slipping force, right, then my box would slip and not tip, right? So that the highest that we can get would be actually for the case of slipping. So let's draw a free body diagram for the slipping case. So we have, of course, our normal force and our friction force. We have our P right here, and then of course we have a weight of the box, W. So now if we want to get P, we need to know what F is. For F, because it's at impending motion, we need N. So let's solve for N first. So we can say sum of forces in the y direction equal to 0 is, what do we get? Minus W plus N. That means my normal force is equal to W, which is equal to M times G. We'll just leave it as M times G for now. All right, so that would be in the y direction. So if I look in the x direction, Fx equal to 0, what do I get there? I get P and I get minus F. Again, let's put our coordinate system here so we know what directions are positive. Now we are at impending motion. Impending motion. That means that F is equal to mu s times n. So we can go back in here. We can say that means P is equal to F is equal to mu s times n. N is equal to m times g. So mu s times m times g. All right. I don't think that will fit here, so let's go to the next page. That would be mu s from the problem statement of 0.5. The mass is 200 kilogram, and G is 9.81 meters per second squared. And that gives me 1/2 of 200 is 100, so 981 Newton. All right, so that would be the strongest force that I can get before my box starts slipping. All right, so now in order to make this box tip, we have to make sure that the force acts at the right height, right? So what we can do is basically we can say that we do another free body diagram, and then we'll do the tipping around the corner. So let's just draw our free body diagram real quick. This is our box. This is our weight. We have P acting here somewhere. We know that this is the height that we're basically looking for. And now, because we know that we're just about at tipping, we know that our normal force acts here and our friction force. And maybe let's just give this point a name. That is point A. All right, so all we have to do then is do the sum of moments around A, right? We know that's 0 because we don't want it to move. It's supposed to be just before it starts moving. So what do we get? F and N both will go through A. We don't have to worry about them. W is going counterclockwise. So it'll be W times half of the width. So it'll be 0, but it'll be 1/2 times 1.2. And then P is going clockwise, so minus P times H. Now P we know, W we know, so we can just solve this for H. Means H is equal to W times 0.6 meters divided by P is equal to M times G times 0.6 meters divided by, if we go back up here, instead of using that value, if we just put in the symbols, right? So it'll be mu S times M times G. That means that M and G cancel, so I'm left with 0.6 meters divided by 0.5, 1.2 meters. So we know that the height that this is acting on would be at 1.2 meters, right? So we go back to this, basically we'd have be almost like a square, 1.2 times 1.2. But again, so the idea is that to find the largest force for this to be tipping, right, has to be the same force as we would get if it's just about to slide, because any force stronger than that would mean that sliding, and we can make it tip or not tip by adjusting the height, right? If this height were less than 1.2 meters, then we would not get tipping. If it's more than that, then it would tip for a smaller value. All right, so this was a quick example about slipping and tipping.